Dear students, I, Mr. Vishal Shah, Assistant Professor, Krishna Institute of Pharmacy, Karad, once again welcome you all to this new session of Instrumental Methods of Analysis, Atomic Absorption Spectroscopy. In previous video, we have finished with the flame photometry, which is also known as the atomic emission spectroscopy. Here we are going to start with the atomic absorption spectroscopy, which is a different one as compared to the, or exactly you can say it's a reverse of the flame emission spectroscopy. Now if you are coming first time to this my YouTube channel, you can subscribe to get the more videos. Also, you can watch the previous videos related to the instrumental methods of analysis. So, let's start with our today's session. Now, first we will see the introduction of the atomic absorption spectroscopy. Atomic absorption spectroscopy is a very common technique for quantitative determination of trace metals. Even we can measure the metals that are available in the parts per million, that is the ppm, then ppt, that is the parts per trillion, and also metalloids in the liquid. So this is the one of the advantage of atomic absorption spectroscopy. It is very reliable and very simple to use. That's why this is the commonly used technique to carry out the determination of different trace elements. It can analyze over different 60 to 70 elements. So wide range of elements, metals can be analyzed by using this technique, due to which it is considered as a very reliable as well as very simple technique for the use. It also measures the concentration of metals in the sample. Means if the metals are present along the conjugation with other elements, if they are present together in sample, in that case also this technique will measure the concentration of metals. The first atomic absorption spectrometer was built by a scientist whose name is Aaron Walsh in 1954. The first spectrophotometer was built, which is based on the principle of atomic absorption spectra. Now this method provides total metal content of the sample and is almost independent of the molecular form of the metal in the liquid. Means, what is the meaning of this? That the form of the metal indicates here that the any form, whether the metal is in bound form or whether the metal is in free form. In any form, this particular technique will carry out the determination of the metals that are present in the liquid. For example, one can determine the sodium content of a water sample, and in most of the cases it does not matter in what molecular form the sodium exists. Now we know in most of the case sodium exists in the water in the form of the NaCl. It is formed the bonding with the chloride, which leads into the formation of the NaCl. Whether the sodium ions or the metal ions are free or whether they are present in the bound condition, in any form, this particular technique will determine the concentration of this metal ion. So this is the one of the advantage of this technique is there over the flame emission spectroscopy also. Further, most common rare earth metals have been determined by using this technique in the range from trace to the macro quantities. As I said, even for parts per million, parts per trillion, concentration also we can use this technique, not for only small quantities, even macro quantities of metal can also determine by using this technique. Also, direct application of this technique is limited to the metals with exception of the B, that is the boron, selenium, arsenic, then several non-metals have been estimated by indirect technique. By using this technique, the determinations can be made in the presence of many other elements. Means suppose if the mixture of metals are present in the given liquid sample, then we can determine only particular one or two metal ions in presence of other elements or the metals also, because the whatever the light that is absorbed by the metals, it is a characteristic to that particular metal only. That's why in presence of other elements also we can carry out the determination of different metal ions. It means it becomes unnecessary to separate the element to be determined from the other elements that are present. So this is the beautiful advantage of this atomic absorption spectroscopy is there over the flame emission spectroscopy. Means there is no need to carry out the separation of the sample. Just directly we are going to put our sample that is present in the liquid form, and automatically instrument will take care of that, and it will carry out the determination of the element of our choice of interest. Then we will see what is the principle involved in this atomic absorption spectroscopy. The absorption of energy by ground state atoms in the gaseous state forms the atomic absorption spectroscopy. If you remember, in flame emission spectroscopy, we have seen once the elements that are present in the ground state, if they absorb certain amount of energy, they will be excited, they will go to the excited state where they will not stay stable because of the energy, and they will try to come to the ground state to get the stable form. And while coming back to the ground state, they will emit the certain amount of light, which is known as the photon. And these photons, determination of the emitted light is the basis of the flame emission spectroscopy. In contrary to that, absorption of energy by ground state atoms in gaseous state, this is the form the atomic absorption spectroscopy. Means atomic absorption spectroscopy is based upon this principle. Now, when a solution containing metallic species is introduced into the flame, the vapor of metallic species will be obtained. Some of the metal atoms may be raised to energy level sufficiently high to emit the characteristic radiation of the metal. Means after absorption of the specific amount of energy, the metal will go to the excited state. The phenomena that is utilized in the familiar technique of the flame emission photometry. Now, but a large percentage of metal ions will remain in the non-emitting ground state. Means the most of the metal ions, instead of going to the excited state by taking the energy, they will try to remain in the non-emitting ground state. Now these ground state atoms of a particular element are receptive of the light radiation of their own specific resonance wavelength. So all metal ions will not go to the ground state. So due to which what happens, to the excited state, due to which what happens, the ground state atoms will carry out they will receive or they will absorb the light radiation of their own specific resonance wavelength. Thus, when a light of this wavelength is allowed to pass through a flame having atoms of the metallic species, part of the light will be absorbed, and the absorption will be proportional to the density, or you can say the concentration of atoms that are present in the flame. So in this way we can carry out the determination of we can use the atomic absorption spectroscopy further. Thus, in atomic absorption spectroscopy, one can determine the amount of light absorbed and not transmitted. Remember, in flame photometry, we are going to carry out the determination of light that is eliminated, that is the photons that are eliminated or transferred, while here we are going to carry out the determination of the light which is absorbed. Now, once this value of light is known, the concentration of metallic element can be known because the absorption is proportional to the density of the atoms that are present in the flame, or the concentration of atoms that are present in the flame. So this is the basis of the principle involved in the atomic absorption spectroscopy. Now mathematically, the total amount of light that is absorbed may be given by the formula at particular frequency. Here this V denotes the frequency. So at the particular frequency, the total amount of light absorbed is given by the formula pi E square divided by mc into nf. Here E is the energy of the electron, which is having a mass m. C is the speed of light. Then n, total number of atoms that can absorb at frequency V. So this is the formula by which one can carry out the determination of the amount of energy that is absorbed by the respective elements. This technique uses basically the principle that the free atoms generated in atomizer can absorb radiation at specific frequency. Atomic absorption spectroscopy quantifies the absorption of ground state atoms in the gaseous condition, atoms which absorb ultraviolet or visible light and make transition to the higher electronic energy levels. The analyte concentration is determined from the amount of absorption. So this is the principle that is involved in the atomic absorption spectroscopy. Now we will see what is the difference between the atomic absorption spectroscopy and flame emission spectroscopy, which is known as the flame photometry. Now we will just revise what we have seen in the flame emission spectroscopy. Now in flame emission spectroscopy, the atoms when put in flame, they become excited. Excited atom, which is unstable, quickly emits a photon of light and returns to a lower energy state, eventually reaching the unexcited state, which is known as the ground state. The measurement of this emitted radiation forms the basis of flame emission spectroscopy. Now analytical signals in the flame emission is the sum of all energies emitted as excited atoms, which drops to the ground state. Now the signal comes entirely from the emitting atoms. Means it's not compulsory that all atoms that are present in given solution will go to the excited state. Sometimes only few amount of atoms may go to the excited state. But in case of atomic absorption spectroscopy, the signal is obtained from the difference between the intensity of the source in the absence of metallic elements present in the liquid and decrease the intensity obtained when metallic elements are present in the optical path. Means here we are going to carry out the determination by using two ways. Means blind solution is also determined, which is not consisting of any metal elements, and also in presence of metal also we are going to determine the absorbance. So the difference will give the exact amount of elements that are present in the given solution. In flame emission spectroscopy, the emission intensity is dependent upon the number of exciting atoms and is therefore greatly influenced by temperature variations. While in atomic absorption spectroscopy, atomic absorption depends upon the number of unexcited atoms and the absorption intensity does not depend upon the temperature of the flame directly. Also in atomic absorption spectroscopy, the relation between absorbance and concentration is merely linear, that is the Beer's law is obeyed over a wide range of concentration. So this is not in case of the flame emission spectroscopy. So this is the difference between the flame emission spectroscopy as well as the atomic absorption spectroscopy. So in this video we have discussed about the introduction part, then principle as well as the difference between the flame emission spectroscopy and atomic absorption spectroscopy. Thank you.